Having been a professor for a long time, I'm delighted to be here at this center activity that incorporates a graduate program. If you could raise your hand, all the students in the room. Outstanding. And so how you combine bioscience and batteries is you start off as more or less an applied mathematician. And so we've had some very interesting journeys in science and mathematics. And today I'm going to talk with you a little bit about solid-state battery technology, which really stemmed from a lot of work we did in mathematics and trying to understand what should be built. And so instead of going from the standpoint of we have a particular favorite material or we have a particular religion about a processing route or a particular compound, we started off really trying to improve energy storage technology. And the reason is that batteries enable really important things. And it's a simple statement, but it actually embodies a lot. Batteries are important in 3 different sectors, and interestingly, the same humble technology, the same 18650 cell. How many of you have seen a battery cell like this? It's 18 millimeters on diameter and 65 millimeters long. And it is in 3 different industries. It's in consumer electronics, it's in automotive, and it's in grid storage. And as such, it addresses billions of dollars in value. Most importantly, though, it affects our lives in ways both simple and profound. In consumer electronics, the market sizes are enormous. Within a few years, we expect to see markets in excess of $4 billion. And principally, that's in smartphones and laptop computers today. And I'll talk a little bit about what the next markets are going to be in a moment. In automotive technologies, we project over $3 billion, and that really depends on when the launching point for electric vehicles will be. How many electric vehicle fans in the audience? I see you charging stations. So I say not if, but when, and I know the people who raise their hands agree with me on that. The reason is not just because generically we want to see clean technologies come onto the drivetrain, but that from a life cycle analysis standpoint, from an economic analysis standpoint, and from a sustainability standpoint, we really think that this is a very good solution to powering personal transportation. And an improbable thing happened in that gas prices went up enough to make it actually pencil to buy a hybrid electric vehicle. How many drive a hybrid? And you're actually doing a good thing for your family finances by doing that. 10, 15 years ago, it was maybe a break-even proposition. Now that's not the case anymore. And so as we've seen market penetration of hybrid vehicles, we think that there's a very strong economic case for electric vehicles if we can get the energy density up and the battery cost down. In grids, most of the world has substandard electrification. Most of the important parts of the world, most of the economies that are going to come online and join the first world economies. And it's interesting how we accomplished electrification in this country was with large public works projects, principally TVA and all that followed. In China, Three Rivers Gorge was an example of that, and it was very similar to how we accomplished our own electrification. What's likely to happen next are smart grids. How many work on smart grids? Okay, and so that's likely to become a more efficient way of doing things. And it's, of course, as a more or less an applied mathematician, I find that very satisfying. But more importantly, it has a potential to bring renewables onto the grid mix more efficiently. What enables that, of course, is energy storage. And those markets, of course, will be large. So batteries don't actually enable everything we'd like to see just yet. And the principal reason is they cost too much. So certainly energy and power density are important, but the cost is presently a little too high to have everything that we'd like to see. This is a kind of a colorful slide in more ways than one. I'll let you just read for a second. People out there on the blogs are very frank about whether they like their smartphone batteries, and they don't, not always. And one of the things that people really complain about, he who laughs first reads fastest, right? But people really complain a lot about the battery cell technology in their smartphones. It's an easy thing to notice, right? It's an easy thing to notice. After a couple months, after 4 or 5 months of using your smartphone, you experience capacity fade, right? It takes longer to charge up. The battery depletes faster. If the battery gets warm, that condition worsens. over time, you're walking around your house or your office with a recharge cord hanging off your battery cell. And the reason for that is complex. There are multiple reasons for the failures inside the batteries that limit its lifetime and performance, but it translates into something that consumers can readily see. By sector, there are different challenges. So in consumer electronics, the today markets are obviously laptop computers and smartphones. Next are wearables, clearly. How many are wearing a wearable device right now? Those are the engineers, right? So wearables are likely to become a very important pathway to connection to the internet. And battery technology is not sufficient right now to enable the small devices that people really want. Wearables are a little bit larger, a little bit less energy dense, and a little bit expensive. So what's needed is higher energy density and high power density. And it's not the expense in this case, because the willingness to pay for a very high energy density technology, a wearable device that you don't have to charge up but every couple of days versus 2 times a day, is actually really high. So people are willing to pay for that, especially in light of the fact that the wearable device itself can be rather expensive. But energy density and power density are very important in that sector. In automotive, by contrast, the today markets are really hybrid vehicles and some production of EVs, but small run productions in general. The next markets, we believe, will be large-scale EVs, so lower-cost EVs, so that everybody can have an electric vehicle. And what's needed there is not only high energy density for range. I mean, that's obvious. Everybody would like to have more range in their, more electrons in their electronic gas tank. More people would like to have range, but most importantly is cost. Battery pack today can cost upwards of $15,000 to $30,000, comprising a huge cost to the vehicle and making it relatively unlikely that we'll see market penetration for economy vehicles. In grid, today there are demonstration projects and microgrids, and there are several municipalities around the United States and in other countries, of course, where there are some combinations, right? Some permutations of renewables, power electronics, electric machines, and energy storage, and various generation technologies. So a genset plus electric storage and plus renewables is a common scheme for that kind of a system. Tomorrow, the next markets are smarter grids that are larger, that can power homes, communities, municipalities at a larger scale. And again, what's needed there is higher energy density and lower cost. And when we look ahead to the grid battery cell is very similar to the auto battery cell. It's a larger capacity system. It has more stringent operating requirements, and it has more stringent safety requirements. So by sector, if you summarize these things pretty simply and pretty quickly, you come to the conclusion that if you have a higher energy density, a higher power density, and a lower cost, you not only enable new products, but you create larger markets. All right, so that's pretty well understood. For those of you who may not recall how a battery operates, here are just a couple of slides to orient everyone. This is on discharge. So on discharge, at the negative electron, there are a loss of electrons. At negative electrode, there are a loss of electrons. The kinetic equations are written down. The anode and the cathode are separated by a separator. And in traditional batteries, today's batteries made by lamination technologies, a liquid electrolyte is used to allow transport of lithium ions from the anode to the cathode on discharge, and from the cathode to the anode on charge. And so in a lithium batteries are sometimes called rocking chair batteries, because rather than have a reaction at the electrodes, lithium actually intercalates into a material that's used as the cathode. And the toolkit for cathodes is shown right here. In the lithium electrochemistry, the cathode is the limiting electrode in general. And so as long as you provide enough lithium, the cathode is the limiting electrode. So the energy density of the cathode is theoretically the best you could do. Make sense? So you're always looking for a higher energy density or a higher gravimetric capacity cathode. And here are some of the common ones. The X in LIX is the number of moles of lithium that intercalate into the cathode material, which is a measure of how much capacity that the battery cell in total will give. So in general, we always look for materials that can intercalate a lot of lithium. And if you hear that, that's why. Now, that's the toolkit, and that's pretty common globally. So those electrode materials, the cobalt oxide, nickel, cobalt, manganese, NCA, iron phosphate, vanadium, silicon, these electrochemistries, to the smaller extent silicon, titanates, are globally scaled already. And in general, they're all made the same way. In a production process that uses porous materials and trained in a manufacturing line where the particles are mixed first in a wet slurry, deposited onto a conveyor belt, and rolled through or pulled through a slot die or doctor blade to a certain thickness, rolled, compressed to shape, a separator is placed over the top, then the anode, which is generally carbon with lithium, and then that whole cell is vacuum filled with non-aqueous liquid electrolyte. And in general, there are 18 or more unit operations or steps in the production path. And the depreciation is pretty high, normally 5 to 10 year depreciation, but at a very high depreciation rate. And the whole battery cost is about $1,000 or more per kilowatt hour. At a cell level, in the industry today, we're seeing about $300 or so for a pretty good consumer electronics battery. That's $300 per kilowatt hour. For a higher end automotive battery cell, $500 to $800 or so per kilowatt hour. And the reason that that cost is pretty conserved across these electrochemistries is that the manufacturing process is very, very similar, and the difference in cost of the materials is not that great. So cobalt's a little bit more expensive than some of the other technologies, which is why it makes sense for the cobalt to be cut with manganese and be cut with aluminum in some of these batteries. But by and large, these cost structures are very similar. The bill of materials, which is the cost of the materials in the battery cell, divided by the cost of goods sold, which incorporates the manufacturing costs, that ratio is also very high. So the BOM to COGS ratio in most of these technologies exceeds 80 and sometimes 90%. So what that means from a manufacturing perspective is that the opportunity to reduce the cost of the device with excellence, with operational excellence in manufacturing is limited, because the great majority of the cost of the battery cell are the materials going into the battery cell. So certainly siting production near a source of material to reduce the cost makes sense. Certainly improving the efficiency in cracking a certain mineral or element out of ore of whatever stripe that you need for the active material in the battery cell makes sense. But by and large, improving operational excellence doesn't buy too much globally in terms of reducing cost. Also, because these battery cells are made in a very similar way and operate in a very similar fashion, the incumbent technologies have similar challenges. They're all made out of compactions of particles, polydispersed systems, which means particles of different sizes. They all have different shapes as well. The cathodes are actually fairly complex. So the cathodes are comprised generally of cathodic particles, which are multiply concave and convex. They're irregular, but they can be approximated, if you like mathematics like we do, as maybe a triaxial ellipsoid. So you can stretch it out to a prolate ellipsoid. Some of the people are nodding because they like math too. So prolate ellipsoid or oblate spheroid, big rods or discs. And you can approximate what the geometry is. The reality is if you put one of these particles under an AFM, they are multiply invaginated. They have lots of nooks and crannies and crevices and so forth. But be that as it may, fundamentally, they're particles of different shapes and different sizes that are crunched together inside the electrode. Those particles are actually coated in general with carbon that's mixed with a binder, a polymeric binder, generally PVDF. And that polymer binder containing the carbon improves the conductivity on the surface of that cathode particle, rendering it to be much, much more conductive and improving the charge density on the surface of that particle so that you get more capacity out of the system. The separator materials, by and large, are dip-coated ceramic coatings on polymer. The anodes are lithium and carbon, and the electrolytes are non-aqueous electrolytes of a very similar toolkit. So We worked on that technology quite a bit. And when I say we, I mean all my great colleagues at every University of Michigan, including Professor Wei Liu and Professor Wei Shi, and I worked on phase changes and stress and optimization together. Professor Christian Listowski at the University of Michigan, have been a collaborator for 25 years. Our favorite collaboration are our two kids, and we work together on life cycle analysis and on a number of different issues in chemistry and mathematics. We had collaborators among, of course, our wonderful students. Some of my students have gone on to become faculty members also, and several of whom already have gotten tenure. Dr. Jung-Hyun Park was a big contributor to some of the work I'll be talking about today, and he's now selecting which faculty position he wants to take, which is marvelous. We were sponsored by the DOE, as Professor Benson has pointed out, and we've also had partnerships with a number of national laboratories, including Argonne National Labs and Lawrence Berkeley Labs and Brookhaven, where we got beam time to do some of this materials interrogation, also Oak Ridge National Labs. And most importantly of all, my collaborators at SAKTI3, a team of truly outstanding men and women. It's an honor to lead the group. And the simulations that we've done at SAKTI3 have guided the innovations we've tried to contribute in the solid state technology. So I'll talk first about the lamination technologies and what we learned from that, and then I'll talk a little bit more about the suite of tools we built to try to get rid of the liquid electrolyte. So 1994, the big three: clothes, homes, and battery models. The clothes were not very good. Homes were McMansions mostly. I mean, most of us probably grew up in houses that look about like that. And then battery models, we thought they were still live in a house like that. That's a nice house. Battery models, what's that?
That's the problem.
That's the problem with all these McMansions. See this energy efficient crowd, yeah. You'll like the next picture better. Okay, so just stay tuned. But battery models at 1994, when we started working on this problem, were really continuum models. And they took a continuum point of view about the battery cell, namely that all of the materials were smooth, homogeneous continua with nice, even intercalation of lithium that led to nice, predictable concentrations from a chemical engineering standpoint, and nice, even discharges. And by their nature, they were semi-empirical models. And the models created by Professor Newman and Professor White were fantastic. I mean, they were absolutely the first step in understanding how to characterize charge and discharge of a battery cell and how to start to think about what kinds of materials to develop. So when we started working on this problem, that was really the state of the situation. Continuum homogeneous models where you would simplify a complex porous electrode on the cathode as a material of known conductivity and diffusivity, a complex anode, again, known conductivity, known diffusivity, and the electrolyte. And assume that all the particles on both sides saw ions and electrons in a smooth wave. The reality, of course, was a little bit different, as we've seen. So a real porous material is very complex. It has multiple materials, even coated materials. The shapes of the materials are actually quite different. They're polydisperse, and not all the particles even have the same shape, let alone the same size. And so when we started to work on this problem, it was clear that existing models allowed prediction of charge and discharge curves and allowed basically to select high voltage electrochemistries, for example, or high theoretical capacity cathode chemistries that would allow you to have total battery capacities that were large. They didn't allow direct incorporation of the microstructure effect. So any porous media people in the audience? So Brueggemann's correction, right? Handy for volume fraction, but it breaks down at very high volume fractions and very low volume fractions. And more importantly, it doesn't allow you to interrogate concentrations of stress, concentrations of heat, concentration of electrons or charge, and concentrations of chemical species. And so even though you can account for changes in continuum behavior by corrections, such as Brueggemann's corrections or other corrections to volume fraction, it really didn't allow us to interrogate how do we select these particles? Should they be polydispersed so we can get high packing fractions? Should be monodispersed? What should be the interparticle spacing? Some of those things you can actually control by selecting materials. And so we really wanted to be able to do that. It doesn't allow, a continuum model also doesn't allow direct interrogation of composition. So when you assume that one electrode or the other is a smooth, homogeneous continuum, it doesn't directly allow you to figure out and do the inverse problem, right? What should be the fractionation of this species? How much PVDF, how much carbon can I tolerate? How much surface area to volume ratio even? Doesn't allow you to look directly at failure. And so there are a lot of pictures like this in the battery literature. Who are our battery people here? I can say whatever I want now, right? Raise your hand higher. Who are all the battery people? Okay, admission, guilty admission. Yes, I know batteries have been the Afghanistan of the business world, but you see a lot of pictures like this. You see a lot of pictures like this. You see a lot of pictures of things that are putative failure mechanisms. We had a question. Where is this failure coming from? Because the manufacturing process actually incorporates large-scale deformations in these particle networks by compaction of the material under large rollers. And so one of the questions we had was, are they breaking before or after you start charging the batteries? And it looked pretty clear to us it was probably some combination of effects, right? It didn't allow you to optimize microstructure. And this is something that we were very interested in doing because there were a lot of possible solutions. So there's no point in modeling something and trying to wish it into existence. There were a lot of groups proposing microstructures, everything from foams, like was done in nickel metal hydride batteries, which were the forerunner to lithium-ion batteries. That was the last generation electrochemistry, all the way up to HIPCO-produced nanowires and nanotubes and other kinds of microstructures. And so what we really wanted to be able to do was write down a set of models where we were solving partial differential equations on the surfaces of those particles so we could decide what kind of a particle microstructure to build. And then, of course, we wanted to be able to understand the manufacturing process effect. To the earlier point, you induce some damage in manufacturing, and we wanted to be able to assess that, and certainly to be able to understand the difference between what we were doing to the materials in manufacturing versus what was happening to them due to intercalation stress. And again, intercalation is when lithium nestles into the cathode and expands. Those can be coincident with very large volume changes, thus very large strains, thus phase changes in the material. So the notion that the oxide that you start with on the cathode is the oxide that you finish with is not right. Okay, material scientists, in the eyes? You know that's not right, right? So if you put a large temperature change or you put a large stress change on the material, you've got a different material, you've got a different phase. And that in turn affects the intercalative properties of the material. So it was important to us to understand where those stresses were coming from, whether they were intercalation induced, whether they were manufacturing induced, and also to understand the failure. So we started to write some papers on mathematics, and this is what I mentioned before on percolation statistics, which is sort of a long time love of mine in critical phenomena and understanding the mathematics of the brink, mathematics of the tipping point, the point at which you have at least one single domain spanning path of material that you can walk continuously from one boundary to another on. And that really is the onset of the beginning of the real change in transport properties. So if I have a material that's non-conductive and I add some certain fraction of another material, at some point, at some volume fraction, I start to be able to conduct, right? And that point is a percolation point at which I have the material, which is the conductive phase, connected. And so the whole reason that people put carbon into battery cells in the cathode is in order to form those single domain spanning paths, in order to get conduction of the electrons. Because when you make a battery cell out of an oxide as the cathode, it's not very conductive. And for the battery cell to work, you need to be able to get electrons out. So you need to add conductive additive to the point where for a thickness, a certain thickness of cathode, I can actually conduct and get the electrons out and drive a load, right? Which is the first picture I showed on discharge. So we were looking at all of these different materials, and there were some closed form solutions for certain kinds of arrays, monodispersed spheres and monodispersed rods and so forth. We wanted to sort of look at everything at once because the shapes and sizes of what was going into the battery cells were quite diverse. And so we first started to write papers about, what happens in monodispersed systems where you have triaxial ellipsoids, where you have very prolate systems, oblate systems, what are the critical phenomena? And then we started to look at polydispersed systems. And then we started to write algorithms, which were called settling algorithms. So we could put spaces in 3 space, points in 3 space, assign particles to those spaces, apply gravity to the whole system, and then start off with something that you could do computation on. Because you can't do computation on something where the particles actually overlap. And so we came up with methods of writing algorithms to build the geometries that we do calculations on. If all of this sounds very painstaking, it was. And I worked with some very, I had the honor of advising some very bright students on the subject. This happens to be Dr. Yen-Hung Chen's thesis work, and he's now one of my colleagues at Sakti3. So we started to look at, okay, if you put into the simulation what's really in the battery cell, can you figure out how to get enough of the conductive additive in order to improve the conductivity? And that was really the upshot of that work. And so we were able to establish some floors on that. How many particles do you need? What shape do they need to be? And as you might expect, if you use the same volume of long, thin rods versus spheres, you wind up with a total mass of long, thin rods, which is lower because they're going to connect, right? And so that's a very short description of what wound up being a very long journey in percolation, and we wrote a bunch of papers about that, and most of them are in Journal of Applied Physics or Proceedings of Royal Society, like that. Then we wrote another set of papers on transport analysis, so understanding diffusion, understanding conduction, understanding heat transfer, and really same physical phenomena. Chemical engineers and material scientists, it's just, and anybody with an undergraduate engineering degree, it's just del squared something equals 0. So the transport phenomena actually submitted to the same analysis. And we wrote some papers about using systems that were long and thin, using spheres, etc. Then we started to take a look at the kinetics. And the classic kinetic approach in battery cells is really the Butler-Volmer kinetics, which is a semi-empirical reduced analysis which enables you to write down the constitutive law, if you will, for a battery cell. And so we followed that same sort of pathway that had been laid out by Professors Newman and White and others, except that we wrote down the kinetic equations for the geometries of interest. And so we began to solve these PDEs on these multiply connected complex spaces. And we wrote several papers on intercalation dynamics for various electrochemistries towards understanding what the relationship was with stress. And how we did that was we wrote down the mechanics equations, which I'll show in a second, with a dilatational term which represented intercalation dynamics. And so that was kind of a neat way of incorporating 2 pieces of the multiphysics into the same numerical framework. This is the mechanics, and again, we have 2 big effects. One is pressure on the system, sometimes uniaxial load, sometimes pressure. And that was due to manufacturing stresses and in some cases due to phase pressure, because when battery cells, how many of you are camera fanatics or have camera batteries? Those tend to be high camera systems. Have you ever taken the battery out and not been able to put it back in your camera because it swelled? You don't take enough pictures for my talk today. You take the camera back? That's a good solution. You're supposed to be environmentally conscious. Okay, so some batteries swell, right? He's laughing because he knows it's true. Batteries swell, and what happens is during cycling of a battery cell, they irreversibly form lower density compounds, and they swell. And normally we ascribe those things to reactions of the electrolyte with the cathode, and it's pretty much what they are. But the bottom line is that swelling in a canister of a battery cell causes a pressure on the face. And in a cylindrical cell, it causes multiaxial stress. In a prismatic cell, it causes a phase pressure. So we wanted to look at that too, because that ends up being really important in electric vehicles. It ends up being important because you have to figure out what the size of the casing is going to be for the batteries, and so for the battery cells. And so understanding what phase pressure had to be in order to keep conductivity high was important. So we incorporated that into the analysis. We also worked out a representation for heat transfer, which allowed us to simultaneously look at resistive heating and entropic losses. And that was important because, again, for phase change, we wanted to know whether we were still cycling the same compound that we had started with. And so we developed a framework around that. And then finally, phase transitions in this part of the talk. So we looked at the stress effect on diffusivity, the flux, we applied mass conservation, and we were able to solve the PDEs on the surface of all these different particles for multiply complex regions. And we wrote a bunch of papers about that. Finally, in optimization, we use surrogate-based methods. And so that's just a robust way of arriving at minimum energy solutions when you write out, generally speaking, a set of partial differential equations which describe physical phenomena, and you're looking for local minima. And then you're trying to either minimize cost or maximize energy density or maximize power density or apply some weighting function to certain objectives. And so what we wanted to do was systematically compare battery performance based on changing what went into the batteries. So it was important for us to develop that framework. And of course, we wrote a number of papers about that as well, and including degradation mechanisms. So to summarize the key effects we looked at over around 20 years or so of work on the subject: dissolution and deposition, looking at dissolving the cathode and its effect on battery cell performance, SEI layer morphology evolution, and gas generation being the principal root causes that we thought of as important in degrading battery cells. Then we thought, this is great, okay? So now we've got a framework, and we can systematically look at the trade-offs between some important parameters, and I'll show you a couple of those. One is ionic versus electronic conductivity. For ionic conductivity, you want the lithium in the cathode to race to, or lithium in the anode to race to the cathode. And then you want it to race right back. You want to recover 100% of it. You want as reversible a reaction as you can. And therefore, you want the ionic conductivity to be very high, right? And so liquid electrolytes make sense on that basis because they tend to have a really high ionic conductivity, in general higher than would a solid, okay? On the other hand, you also want the electronic conductivity to be high. And so you want the electronic conductivity in the cathode to be high. That suggests you use a high degree of conductive additive, and maybe you have a lower porosity, which gives you less room for your multiply connected electrolyte. So these two things tend to be at odds in a real battery cell. And we started to look at, okay, for a certain porosity, what is the normalized effective ionic conductivity against the diffusivity? And we identified ranges for those volume fractions which would appear to make sense. Clearly there was a trade-off between ionic and electronic conductivity, and ionic conductivity increases with increased porosity in general. We also looked at energy and power. And so for a high power system, students in the room, what do you think you'd want? A very thin electrode or a very thick electrode? Why?
There's resistance in going through the electrode.
Precisely. You don't want to deal with all that resistance, right? You want to get the electrons and the ions out fast. And so thin makes a lot of sense. It's all surface area, right? Everything's sitting right there on the surface, very accessible, right? For energy, you want the reverse, right? You want a really high capacity, and you want to reduce parasitic masses. So you don't want to pay for things like a large amount of electrolyte or a huge separator in your system. You don't want to pay for any parasitic masses. You want a nice, big, thick electrode. Again, you're at odds, right? And so looking at the trade-off between energy and power was very important. And typically in commercial cells, you'll see cells advertised as either high power or high energy, but generally not both, for that very reason, because the thicker electrodes tend to be the energy cells, the thinner ones tend to be the power cells. We looked at specific energy against specific power, and again, for cathode thicknesses, identified where you would find commercial sweet spots, where you would find combinations of specific power, specific energy, and cathode thicknesses. It sort of made sense. And then finally, one other example, improvement possible in reducing mechanical failure. So presuming that mechanical failure was, by classical fracture analysis, an initiation phenomena where you would have a small penny-shaped crack of infinitesimal size that at a certain strain becomes a growing crack, right? So it's classic fracture analysis. The idea was to figure out how small of a particle you can have such that your strain never gets big enough to grow a crack. It's not that you'll never have cracks, it's just that it won't reach the critical size. And so we identified some ranges, and it turned out that there was a small enough particle where you were unlikely to get propagation of failure. So that was handy. So these are the key findings from us and others. First, there were limitations in particle shapes and improvements. Second, that there were limitations in terms of conductivity and reduced energy. And third, there were optimization results were indicating that we didn't really expect to see much more than a 20% improvement in energy density or power density or the like. So that wasn't as good. We had begun this journey hoping to really look at how much things could be improved, with the thinking being, okay, with the 5-volt materials coming online, with very, very high energy density cathode particles, can we reduce some of the conductive additives and really see a generational change? And we really weren't seeing that. So the result of that was that we really felt we needed a new development path for significant improvement in battery cells. And so now into what we think of as the interesting part, the best way to build a battery if you could do it at low cost. So you have a number of choices, 1D, 2D, and 3D. Generically, we can think of a 1D material like a rod, and you could distribute the active material like a 1D object. 2D would be like a plate, and 3D would be sort of a sphere. And in the limit, where you have all of the active material in 1D, it's really a thin film, right? Because that's a 1D phenomenon. You're moving right in the Z direction in the film. Okay, so you can think of 1D, 2D, and 3D in that way. You can do a thought experiment with geometries defined then. And the thought experiment is like this. Suppose I distribute the active material as a sphere, a rod, or a plate, a thin film, 1D, Z direction only. Can I calculate the diffusive properties and the packing fractions that tell me which is the fastest horse to ride? What's the path to really deliver on? Because as you saw in this picture, oops, not liking that too much. Right. I love that, nano flowers, right? You can make just about anything at the nanoscale. And so with all these choices, we wanted a framework. And this is actually a paper that we're just finalizing now, Dr. Park, Professor Liu, and I. So here are the diffusion equations and boundary conditions, and they're pretty standard. You have a flux at the outside of the object and nothing at the inside, right? No flux at the inside. And you look at diffusion as it moves through the object, as a sphere, as a rod, or in a plate in the Z direction. You can quite readily and directly calculate the volumetric capacity. Assuming some diffusion, right? Assuming some diffusion coefficient, you can quite readily calculate what happens to a sphere in a box, a cylinder in a box, and a cube filled with space-filling material, right? Bless you. And then you can quite readily calculate what the diffusion limited capacity is. Now, it's a little bit obvious that for this case, for really small particles, in the limit as your particle dimension goes to epsilon, right, or epsilon goes to 0 even, they all look the same. Okay, for really little particles, doesn't matter if they're rods or spheres or thin films, it's all the same. As the particles get bigger, as the thin films get thicker, though, the differences start to emerge. The other thing to look at is that as the C rate, as the rate of charge and discharge increases, there are also differences. And the thin films don't look as good, right, because you can't get across them. They're too thick, right? If you increase the diffusivity in this example, in this little thought experiment, by 10x, the differences start to disappear. So if you develop on the path where you have improved diffusivity, all of a sudden the differences between these nanoarchitectured materials and the thin films are not as significant. But there's a wrinkle. It's not just diffusivity that matters, it's also packing fraction, because you can't have a space-filling system of rods, and you can't have a space-filling system of monodispersed spheres. Okay? You're limited in how many you can pack in. So when you factor that in, the analysis reverses, the result reverses. And actually, the highest capacity system is the thin film for the low and mid-range thickness. And the sphere is actually the worst in those two cases. Okay? If you then develop along the line of making a more diffusive system, your thin film almost always wins. So when we asked the scientific question, what path should you develop on, we said solid state, okay? And work on the diffusivity. The other thing to note about this calculation is that these numbers are for lithium manganese oxide, which is a very typical cathode material and used globally today. And the C rates are, C over 10 is normal for consumer electronics. C rate is very fast for consumer electronics and sort of normal for cars. And a 10C is about the highest that you'd ever really ask a battery to do. Most of that high C rate can be accomplished with S&P configurations rather than simply discharging a single battery cell at a very high rate. So this is really a very practical set of projections. And this is why we are working on solid-state batteries. So thin film today really had its genesis at Oak Ridge National Labs with John Bates and Nancy Dudney, who's been a collaborator of ours. And at Oak Ridge, starting in about 1991, there were a number of different cathode electrochemistries that have been explored. There are a few companies doing this now. Most are making very small batteries, and most of the incumbents are also working on the cobalt oxide system. It's challenging to do this cheaply. And so the other thing we decided to work on when we started a company was doing it on a low-cost manufacturing platform. And interestingly, when we project the price, it's millions and millions of dollars per kilowatt hour. So here was the riddle. You want to take what's good in today's commercial systems. Everybody's seen videos of laptop fires, probably on YouTube. Well, maybe you look at different things on YouTube than I do, but you might have seen a picture like that. That in itself is not so bad. You can put a system over that to make that system safe, right? So we do that all the time in engineering. We start with things that might be intrinsically unsafe, and we build systems over them. We build controls, we build mechanical systems, we build fire suppression systems, and so forth. So that's not so big of a deal. The cost, though, is a big deal, because the cost of the cell alone for a high-end system is $500 per kilowatt hour. When you put all of the system costs over that, it's actually quite expensive. The R&D solid-state demonstration projects were producing battery cells that really were very high energy density and very high cycle life, but very expensive. So what we wanted to do was use modeling to optimize cells and pick a low-cost manufacturing route. To have real impact, we need to make them cheaply. So today, clothes are a little bit better. You like that picture better? Their houses are greener. He likes that better. And modeling is multiplexed. So it's not really enough just to look at smooth, continuum, homogeneous models of battery cells. Actually, in order to make them cheaply, you have to go all the way downstream to be able to do up to and including plant optimization and financial forecasts. And every single step that you choose to integrate as a unit op into the process has to be cheap enough not to break the bank, right? Otherwise, you'll stay in R&D. So that was important to us. So Sakti3 built a new suite of computational tools, which span multi-physics, cell optimization, battery optimization, state of charge estimators, production modeling, financial modeling, and finally life cycle analysis, which is the last thing I'll talk about. So R&D codes had some elements of all of these. Commercial codes had some elements of all of these. What we did was put them together so that the handoff at each step, and it's harder than it sometimes sounds to do, to make sure that everybody's using the same notation, everybody's handing off the same variables, and you do enough tests every time you make a change in one piece of code so that an error doesn't propagate. So it's actually very challenging to incorporate all these areas of science and mathematics, but that's what we set out to do because we knew when we got to that bottom box, we wanted these products to make sense. So we built design codes: cell performance, cell optimization, state of charge estimation, and battery optimization, plant optimization, battery cost forecasting, and life cycle analysis. And these are what we projected. So we looked at about a dozen different electrochemistries before settling on the first one we decided to work on. And we projected pretty big improvements in energy density, which was our #1 thing to work on. We also did a lot of optimization of thicknesses of the components before we ever started manufacturing anything. So, but before we ever started prototyping anything, we started to run the codes to figure out how thick and thin things needed to be, how fast we needed to produce them, et cetera, et cetera. And then we started building prototypes, and we continued to build the codes as we built the prototypes. Building them cheaply using the computational results. So rather than drop down a rabbit hole, which was the concern that we'll drop into a system that can't make it at scale, we wanted to make sure and only execute prototypes that actually could be scaled. So this is the generic process methodology. Substrate, current collector, cathode, electrolyte, anode, anode current collector, and an interlayer, and then repeat. And the cells are stacked to make stacked battery cells. Using this kind of a process, you can actually dismantle some of the cost structure. The device methodology is like this: thin electrodes in the micron range rather than thick electrodes in the hundreds of micron range, pursuant to the discussion earlier that you want to have high enough diffusivity and conductivity to make for a high enough energy and a high enough power cell, and no additives being required. That's sort of a boundary condition, because if you start doing things like putting platinum into your battery cells, you're not going to make them cheaply enough so that everybody can have an electric vehicle. This is a simulation. Thick cathode, high rate. So what we really want is red. We want that cathode to be fully utilized. And a thick cathode at a high rate is not fully utilized. The lithium never makes it to the back end of the cathode. What does that mean? Wasted a bunch of material, right? You might as well have just saved yourself half the material cost of the cathode. That was stupid. You never even got to the other side. So you want to design it perfectly so that you've utilized the cathode completely, right? A thick cathode at low rate, all red, okay? That's fully utilized. And so thick, thin, high rate, low rate, we ran lots of recursive calculations to optimize the battery cell's dimensions to accommodate the load profiles that we thought were important. And we also developed some other unique capabilities. On the left is one of our battery cells on test. The engineer breaks it in half, and she breaks it in two, places one part on the table. The part that's still on test keeps cycling. It's kind of handy, right? And then she's going to put the probes on the part that's broken on the table, and it still has a voltage. So I would not recommend doing that with a battery cell on your smartphone, because the liquid electrolyte will all come out of it, and it's not very safe. In the movie on the right, a battery cell, one of the Sakti3 battery cells packaged with our inline process, is dunked into a jar of water. Okay. Briefly, the voltage drops because the leads short to each other because the water is minimally conductive. Battery cells pulled out, and the voltage comes back. So again, capabilities, things that you can do in solid-state battery cells that are difficult, if not impossible, to figure out how to do with the incumbent technology. In addition, these cells have very, very high energy density. So this is one of our champion cells showing over 1,000 watt-hour per liter, which is approximately double what's in the marketplace now. So you get very, very high energy density, good safety, and some unique properties. So we think that that's an appropriate new development path. These are data from Panasonic showing that battery cell energy densities have approximately asymptoted, right, over a couple and a half decades worth of development work. And that fits with what we understood to be happening based on our simulations. Solid state is a completely different development path. So if you had a great material, make it into a solid state battery. Now the big question, which is cost. So can you do it cheaply? This is our cost roadmap for consumer electronics. We project that we should be able to get under, at scale, $100 per kilowatt hour. And that's with reasonable assumptions for consumer electronics cell. We see the same thing in automotive and in grid. So the CapEx for the plant is higher because you're making bigger battery cells. The CapEx to revenue is higher. But we should be able to come under in cost. So then you might ask the question, well, how soon can all of this happen? How fast can new technology scale in batteries? And the answer, as we see it, is pretty fast if the technologies have the same manufacturing platform. Now, people complain a lot about batteries. I mean, we're for that, of course, but people complain a lot that there haven't been new breakthroughs in 20 years, 30 years, and so forth. But actually, if you track what happened in new electrochemistries, it actually hasn't been all that long. If you look, for example, since the invention, or really, of lithium cobalt oxide, 31 years until it was scaled globally, and it's an expensive technology. The iron phosphate, 16 years or so, and NCA and NMC, 12 years. And so from the invention of materials that were higher energy density to scaling globally actually happened pretty fast. And part of the reason was there was an established supply chain. Batteries are all basically made the same way. So that's not to simplify a lot of hard work that was done in training new materials and new processes into plants, but just saying generically the supply chain was already in place. Replacing all the batteries on the planet with improved batteries is a lot of batteries. And so one of the things that we worked on at Sakti3 and we continue to work on in collaboration with University of Michigan and Professor Ostosky is life cycle analysis. This is one example for battery electric vehicle mobility, starting with BEV miles driven, roadways, vehicle operation and maintenance, drivetrain, battery, glider, and the materials in the battery cell. So moving down in scale, adding up the contributions on indicators ranging from carcinogens, teratogens, or bioaccumulation. So looking at, in life cycle analysis, in a holistic way, and engineeringly, in a proper way, we wanted to understand what was the effect on sustainability. So if everything were to flip to battery cells, and specifically solid-state battery cells, what would happen? So Professor Ostosky's group collaborated with, we just gave data, they did the analysis, but the cumulative energy demand index global warming potential for solid-state versions versus laminated versions for a few electrochemistries show that actually not only are laminated battery cells from a life cycle analysis favorable over an IC engine-driven drivetrain, but the solid-state versions are even better. So that's gratifying. And part of the reason is that the solid-state versions are so much more energy dense. It's not only because the materials can be entrained more readily and be recycled more readily, we think, but also just because you're kicking out more watt-hour per liter from a plant. So to conclude, it's a lot of batteries. We think that solid state has a very good development path going forward. I certainly hope that everybody in the room working on your own technologies will start to think in advance about these issues prior to working on inventing a new technology. When I was a young engineer at DuPont, the plastic bottles had a large unintended consequence. And the inventor of those plastic bottles spent the last 10, 15 years figuring out how to recycle those plastic bottles, right? It would be great if everybody in the room, and I hope we'll be successful in this, I hope you'll be successful, sort of thought about these things up front, thought about the life cycle analysis up front. And the reason in the case of batteries is that it's a huge, huge set of markets, just enormous. 6,800 million mobile cellular subscriptions, 90 terawatt-hour per year. In vehicles, 7,600 terawatt-hour per year just in energy use, just in the United States. And that's dwarfed by the global figure, which is 29,000 terawatt-hour per year in energy use. So the way in which these materials are recovered and recycled and the importance of establishing a profitable means to recovering those materials cannot be overstated. So to conclude, these are the tenets of our company. This is what guides us. And I want to say thank you for having me. Thank you very much.
Thank you. So we'll now take questions. We start with the students. That's our tradition here. So any students who have questions? Yeah, go ahead.
So for solid-state battery, I guess that the discharge rates would be a little bit slower compared to, say, a liquid electrolyte. How much, if it is slower, how much slower? And does that limit your applications? And then, if so, like, what is really kind of the most favorite application for solid-state battery?
So that's a great question. So the discharge rate that you can achieve with a solid-state cell and still have a reasonable capacity is different There are a couple of system solutions to that. So one is certainly to make a thinner electrode, and as you saw in the simulations, that's certainly possible. When you make a thinner electrode, of course, you suffer from a greater fraction of parasitic masses in the material because you can't necessarily rescale the electrolyte as you rescale the cathode. That said, we've demonstrated very high powers with these battery cells, higher than what's in the marketplace, and also for sustained power. So rather than pulse power, which is different, pulse power would be a very rapid discharge, and you really wouldn't intend to fully utilize the cathode. In this case, you can sustain it. So that's one thing, thin out the cathode. Another thing to do is change the S&P configuration. Actually, you can use a system solution to solve this because the reality is in vehicle technologies, you don't need sustained power. It's normally pulse. And so it's a reasonable solution is to mix high power cells and high energy cells, so long as they both operate. And you can change the operating bus voltages in your pack quite readily so that you route the power from the power cells when you need it and from the energy cells when you need it. Does that help?
Yeah.
Building on that question, I'm curious what the limiting factor in power density is, and it sounds like it's the ionic conductivity of the cathode, and I'm wondering if that's right, and if the electrolyte is a limiting factor at all in its conductivity?
So in the lamination systems, the ionic conductivity is usually not an issue because it's very high, it's a liquid. In the solid state systems, the electrolyte is the separator. And so the ionic conductivity through the electrolyte is important. We don't think of there being a limit in terms of power that you can get out of the battery cell. We think of the limit being power density. So you may thin out the cathode, but you may not be able to proportionally reduce the other parasitic masses. But by and large, we see better power capability in solid state than the lamination technology. Another thing I will point out is that in the lamination technology, one of the things we grappled with when we were working on this technology to try to improve it was dissolution of the cathode. And that was aggravated at high rates. And so that is straight up a kinetic effect. The faster you discharge and recharge the battery cell, the more you off-gas proportionally nitrogen and hydrogen, the more you dissolve the cathode. In a solid-state battery cell, that's not the case. You don't have those side reactions to contend with. So you can hybridize the pack, you can change the geometry. Those options aren't necessarily open in the lamination technology.
Okay, any more student questions? Yeah, okay, go ahead.
Hi. So for the manufacturing process, do you have to break the vacuum in order to deposit different layers of the material, like cathode, electrolyte, and anode? Because normally, you can break the vacuum, you have to pump it out again, right?
Yeah, and so that increases the production time. You don't have to break vacuum.
Okay, all right, okay, let's open it up to anybody. Yeah, okay, we'll start over there.
I think Tesla is planning to make a lot of batteries. How do you look at that? They seem to make enough batteries for the whole world or something like that.
I'm for it, of course. I think, and quite seriously, I mean, when you look at the sizes of these markets, all right, with every technology innovation, there's going to be some orphan capacity. It's normal. It's always going to happen. Seeing what we're seeing now, which is the ecosystem get built for battery electric vehicles, charging infrastructures and the like, is wonderful. It's a wonderful platform for technology advancement because it means there's a floor under the marketplace, which is great. Now, in terms of the lamination technologies, yes, there have been some pretty big numbers thrown down in terms of what the requirements are. I hope they're realized. I think that would be great. I think the real question is, with the technologies that might come next, and there's always something that comes next, right? There's always something that comes next. Is it manufacturable at scale? What we're working on is something that can scale quickly because we use technologies which are similar to the technologies used to make things like food packaging, like bread wrappers and things like that, that are already scaled globally. So by showing the pictures of the map, this is how we were thinking about, okay, can we scale it fast enough to meet the need? And certainly there would be many players in this space, and that's great. It's too big of a set of marketplace for one company probably to handle, but hopefully that helps.
Okay, I think we need to wrap up, so thank you very much. That was fantastic. Thank you.